Okay, so let's now move on towards the second theorem, second circuit theorem that we will be discussing, and this is the source transformation. Previously, we have seen that we cannot calculate the current across a voltage source, and similarly, we cannot calculate the voltage across a current source. But there are scenarios in a circuit where a voltage source can be converted into an equivalent current source and vice versa. But do remember, every voltage source cannot be converted into an equivalent current source, or every current source cannot be converted into an equivalent voltage source. This is only possible when certain conditions are met in the circuit. What are those conditions? That uh, It refers to the interconversion of voltage and current sources, and it states that a current source, and always remember that we are talking about only those current sources which have a parallel resistance with them. That is a current source in parallel with a resistance, right? A current source in parallel with the resistance can be converted into an equivalent voltage source with the same value of resistance, now to be connected in series. If the voltage source does not have, if the current source does not has any resistance in parallel, then it cannot be converted into the equivalent voltage source. Always remember, only those current sources which have a resistance in parallel with them can be converted into a voltage source, and the magnitude of the voltage source we can find out easily by using Ohm's law, that is V is equal to IR, and there is a series resistance of the same value with the voltage source, right? Similarly, the converse of that is also possible, that whenever we have a voltage source and only those voltage sources which have a resistance in series with them. When you are talking about voltage source, now we have a when we have a resistance connected in series with them, then only those voltage sources can be converted into an equivalent current source, right? So similarly, a voltage source in series with a resistance can be converted into an equivalent current source. And now this is important, that with the same value of resistance now to be connected in parallel. And we know that the magnitude of the current source we can calculate it by the help of Ohm's law, that is I is equal to V upon R, or we can say that the current is the ratio between voltage and resistance, right? But the important thing in this topic is that yes, source interconversion is possible, but it is not always the case. Only if a certain criteria is met, then the source conversion is possible. Otherwise, you cannot convert a voltage source into a current source or vice versa. Okay. So now, once we are done with the statement of this theorem, so let's take a look at 2 or 3 examples of this theorem. Okay, so let's look at the first example of source transformation theorem. The statement of question says, let me just adjust it. Okay, the statement is, find the current through 4 ohms resistance for the circuit shown in figure below, right? Find the current through 4 ohms resistance for the circuit shown in figure below, right? So let me draw the circuit now. We have a 2 amperes current source with a 5 ohms resistance, another 5 ohms resistance, this is a 4 ohms resistance, then we have a 10 ohms resistance with a 20 volt source, right? So this is our main circuit, and here in this circuit you can see that we have two sources and we are required to determine the current through the 4 ohm resistance. Let's name this current as current I, right? This is the current I, and we are required to determine this particular current using source transformation. So the first step, we can see that we know not all voltage and current sources can be converted. Only those sources which meet certain conditions can be converted into their equivalent ones, right? So here we can see that we have a voltage source of 2 amperes, and yes, this voltage source is in parallel with the 5 ohms resistance, so of course it can be converted, it meets the criteria. Similarly, we also have the this one is a current source with a resistance in parallel, and yes, it can be converted since it meets the criteria. Secondly, we also have a voltage source which is in series with a 10 ohms resistance, and again it meets the criteria. So both the sources in this particular scenario can be converted. So we will write converting the voltage sources, converting the 2 ampere source into its equivalent voltage source, right? And now let's do this conversion. So now we are converting the source, and let's redraw the circuit. Here we have this 2 ampere in parallel with 5 ohms. That means this complete source will now be converted into a voltage source, and in series with the same amount of resistance, that is 5 ohms. The rest of the circuit will remain the same, right? So this is 10 ohms, this is 20 volts plus minus, and then now one thing that you people must have noticed, that I have placed these polarities in an opposite manner, right? The polarities in the main circuit in the already existing voltage source are different. How the polarities are assigned based on the direction of this current. We know that the conventional current we are talking about, in the circuit this current flows from the positive to the negative terminal, but within the source, when we are talking about within the source, this current flows from the negative to the positive terminal, right? Which means that the place where there is an arrow head, so the positive sign comes in place of the arrow head, and the negative polarity comes in place of the arrow tail, right? If we have an arrow in this direction, then the tail is representing the negative sign and the head is representing the positive sign. Similarly, if is in this direction, then it will be like this, and so on. So understand, and the vice versa is also possible. When you are converting a voltage source into a current source, you also need to take care of the polarities, that the current direction within a source is from the negative from the negative to the positive terminal, right? And if you are talking about the current source, it's of course from the tail of the arrow to the head of the arrow, right? So the magnitude of this source will be V is equals to I times R, and how much was the current? 2, and the resistance was 5, so its magnitude will be 10 volts, right? So I hope this is clear now. again we can do one thing. Again we can apply the same source transformation theorem to this circuit. Here we can now see that we have a voltage source of 10 volts now in series with the circuit, and we also have a voltage source of 20 volts in series with a resistance, right? So both these are in series, so and both these meet the criteria for source conversion also, so we can convert both of them. So let's write converting the voltage sources into current sources, into current ones we can also write. So what will be our equivalent circuit? Our equivalent circuit will be like this. We have this voltage source, it will now be converted in the current source with the same value of 5 ohms resistance, now to be connected in parallel. And here you can see that these two resistances are in series, right? These two, these two resistances are in series, so I can solve them 10 ohms and then perform the source conversion. That's the point here, right? So what it will be like a current source. Again, the direction of current source will be based on the polarity, right? And 5 plus 5 is 10 ohms, and since we have now converted the voltage source into a current source, so this 10 ohm resistance will now be in parallel, right? Again 20 volts and 10 ohms, so the 10 ohms resistance can now be converted in parallel, and the polarity will determine the direction of current, right? So here you can see again it is 10 ohms. So now I is equal to V upon R. So how much was the voltage? It was 10 divided by the resistance was 10, so the magnitude is 1 ampere. Similarly in this case it's I is equal to V upon R. It was 20 divided by 10 is equal to 2 amperes, right? So I hope that there is no confusion up to this point. And now coming towards the next step, many of you might have wondered that why am I ignoring this 4 ohms resistance, and I will continue to ignore this 4 ohms resistance in the next step also. Why is it so? Because we are required to calculate the value of this 4 ohm resistance, and even though you can see that this 10 ohm, 4 ohms and the other 10 ohm resistances, all these three are in parallel, but I will not solve this 4 ohm resistance. Why? Because once I solve this 4 ohm resistance, and I know that the current in a parallel circuit does not remain same, so the branch across which I need the branch through which I need to find the value of current, that branch will be vanished, that branch will be solved, that branch, since that branch will no more remain in the circuit, so how can I find the current? Understand? So in the next step what I am going to do is that I can see that this 10 ohm resistance and this 10 ohm resistance are in parallel with each other, plus this 1 ampere and 2 ampere source are also in parallel with each other, so we can add them taking care of the direction. Since these are in opposite direction, which means they will be subtracted and the sign of the source with higher magnitude will remain, like 2 minus 1, right? So we can write here, this is the equation, right? Solving the current sources and resistances in parallel, right? So is first of all will be equal to, here you can see it's 2 amperes minus 1 ampere, it is equal to 1 ampere, right? And our equivalent will be equal to R1 R2 divided by R1 plus R2, that makes 10 multiplied by 10 divided by 10 plus 10 is equal to 100 divided by 20 is equal to 5 ohms, right? So if we draw the equivalent circuit here, it will now look like this, that we have a current source, and again do remember that the sign of the source with larger magnitude will prevail, right? So we have a 1 ampere current source with a 5 ohms resistance, and then we have a 4 ohms resistance, 4 ohms resistance across which we need to find the value of current I. And now it is clear that the 5 ohm resistance and 4 ohm resistance are in parallel, so CDR is now applicable. So we can apply CDR and calculate the value of current. So let's solve it. Applying CDR, let's name the resistances as Rx and Ry, and since we are calculating the value of current through Ry resistance, that means I will be equal to the opposite resistance divided by the sum of resistances multiplied by Is. So that makes I is equal to 5 divided by 9, which is basically 5 plus 4, multiplied by 1, and the value of the value of I now comes out to be, it's 0.56 amperes, right? So its answer is 0.56 amperes. So let me repeat the question again. This was the given question here, that you were supposed to find the value of current through 4 ohms resistance, and the circuit was provided, and here you can see that we had a voltage source which had a resistance in parallel, and then we had a we had a current source which had a resistance in parallel, and then we had a voltage source which had a resistance in series. So both these sources were eligible for conversion. We just decided to convert the current source first. Conversely, you can also convert the voltage source, there is no issue in that. And then we solved these two resistances in parallel in series, so we just added them, and then we converted the voltage current sources into the voltage sources, and finally we solved the resistances as well as the current sources in parallel to get the final value of circuit like this. We can also apply nodal analysis to this circuit, but we saw that since two resistances are in parallel and there is a current source, so the best possible way according to me was to apply current divider rule. So I just applied current divider rule and found out the value of current to be 0.56 amperes, right? Okay, so let's move on towards the second example, and this is the last example for this topic. The question for this example is, let me write it down. The question says, using source transformation, determine the current and power of 8 ohm resistance, right? The question says, here is the question, it says, using source transformation, determine the current and power of 8 ohms resistance, right? So let me draw the circuit again. We have a current source of magnitude 3 amperes with a resistance in parallel, and the value of resistance is 10 ohms. Then we have another resistance of 8 ohms and 6 ohms. And one more resistance of 3 ohms, and then a voltage source of 15 volts. Right? So again, if you look at this question, you can clearly see that there are two possible scenarios for source conversion, and we need to find the current through 8 ohm resistance and its power, right? So let's name this current as current I, and we can see that the current source has a resistance parallel to it. Similarly, the voltage source also has a resistance parallel to it, so we can convert both of them. So let's write converting the sources, right? And since we are now converting the current source, so we need to assign it a polarity in a similar manner, means plus. So let's now first convert the current source, which has a resistance in parallel of 10 ohms, into its equivalent voltage source. And do remember that the positive polarity comes at the head side of the current source and the negative polarity at the tail side of the current source, right? So and the 10 ohm resistance, which was in parallel, will now be in series, and then we have this 8 ohms resistance, and finally we have, okay, sorry, I forgot to write the value here, it's 6 ohms, right? And then the series resistance will now be connected in parallel, and the voltage source will be converted into a current source with how much value that we will see. Now the value of the voltage source we know can be determined by the Ohm's law. V is equal to IR, and it's 3 multiplied by 10 is equal to 30 volts. And similarly, the value of current source is equal to I divided by V upon R is equal to 15 upon 3 is equal to 5 volts, right? So I hope it is clear to you all. And so now we can easily see that although we can solve this circuit, this 10 ohm resistance and 8 ohm resistance are in series, but again solving them will create an issue, right? So but if we solve them in series, then the 8 ohm resistance will be gone, so that can be an issue. So the first thing that we do is let's solve this 6 ohm resistance in parallel with the 3 ohm resistance, right? And simplify the circuit. So let's redraw the circuit again. And one more thing that we can do is just to have two steps directly. We know that once this value will be solved, the resultant will also be in parallel with this current source, right? So we can solve it directly, or let's just not solve it directly. Let's take a bit of time and redraw the circuit. So the circuit will now look like this. We have a 10 ohms resistance, and then we have a 8 ohms resistance, and finally we have a resistance. This is how much? Plus minus 30 volts, and this value we will be calculating. Now we have this is not 5 volts, rather this is 5 amperes, and here we have to calculate the value of resistance. We know that R equivalent is equal to R1 R2 divided by R1 plus R2. So R equivalent is equal to how much? It's 6 multiplied by 3 divided by 6 plus 3, that makes 18 divided by 9 is equal to 2 ohms. So R equivalent here is equal to 2 ohms. Now we can see that the 2 ohm resistance and the 5 ampere resistance, these are now in parallel. These are now, if 5 ampere source and the 2 ohm resistance, these are now in parallel, so we can convert them into a voltage source. What will be the advantage of converting them into a voltage source? That then we will have a single loop in the circuit, and once we have a single loop in the circuit, simply we can apply mesh analysis and calculate the current, right? That is why we are doing that. So just write converting the current source, right? So we are now going to convert the current source, and so first let's redraw the circuit. This is our volt source, with the 8 ohm resistance. This will be the 2 ohms new resistance now in series. Why in series? Because we have converted this current source in parallel into an equivalent voltage source, and then we will have a voltage source in this direction, right? And this circuit is now completed. What will be the magnitude of voltage source? Here you can see that V equals IR. How much was the current? It's 5, and the resistance was 2 ohms, so the magnitude of voltage will be 10 volts, right? Now you can see that the current I is flowing here, and it's the same as the loop current, right? So we can assign polarities here, and applying KVL to the loop, it will give minus 30 plus 10I. We know that the voltage is the product of resistance and current, plus 8I. Here 8 is the resistance, I is the current, plus 2I plus 10 volts. Why plus? Because it is now entering the positive terminal, right? So equals to 0, that makes 10, 18, 20. 20I is equal to 20, which means that I, it's only I, is now equal to 1 amperes, right? So this is the final answer. And now we have now solved this circuit using superposition theorem. So that's like a quick revision of this numerical. We were required to find the value of current I in this circuit, and we were given the circuit in such a scenario that there were two sources and both of them were eligible for interconversion. So we first converted the voltage source into the equivalent current source, and first converted the current source into its equivalent voltage source and the voltage source into this equivalent current source. We solved two resistances in parallel, and then we again converted the current source into the voltage source. Why? Because the resulting circuit had only one mesh. So we applied KVL to this loop or mesh and found out the value of current through the 8 ohm resistance to be 1 amperes. One more thing that we were required to find in this question was the power of the resistance. We know that power is equal to the product of voltage or current, or the product of square of current and resistance. Once we know the current, it's 1 square multiplied by 8. So the power will be equal to 8 watts. The power of the resistance is equal to 8 watts, right? So in this week we have covered two circuit theorems, the superposition theorem and source transformation theorem. In superposition theorem we learned the concept of linearity and how can it be applied to calculate the voltage or currents in a linear circuit. And in source transformation theorem we learned how a voltage source can be converted into a current source given it meets certain conditions, and similarly how a current source can be converted into its equivalent voltage source given that it meets certain conditions, right? We have two theorems left, Norton's theorem and Thevenin's theorem. We will be covering them in the next week hopefully, and till then it's goodbye.